My name is Tobias Kehokapu, and my project is an analysis of the MOSFIRE data in the Keck Observatory archives. And my advisor this summer was Dr. Jehan Kartalto. So the goal of this project was to organize and analyze MOSFIRE spectra. I was specifically looking at the Keck Observatory archives database, and essentially I wanted this to be easily accessible data and essentially just a catalog of maps accessible to scientists and citizens alike. I want this in the future. I want this to be kind of like an introduction to astronomy and whatnot. In high school, I know astronomy wasn't really big, and I just want this to be easily accessible than just like Googling random things to try to get into astronomy. I want this to be a good like base start to what astronomy is like in the real world, instead of just like, oh, name the 8 planets. Oh, what's the 9th planet? But yeah, I just want this to be a lot more user friendly for anyone just willing to get into astronomy. So the Keck Observatory is the observatory that I got all this data from. It's located at my home state in Hawaii on Mauna Kea. And a little bit about Mauna Kea, it is the best place for astronomy. That may be opinion of mine, but I think it's fact, particularly because of just all the environmental things going on there, because of its high latitude or high elevation. There's little to no cloud coverages on most of the nights up there, which makes it super ideal for astronomy. Because of the dry climate up there, it makes it really good for spectroscopic data. And really, because it's so far away from any big cities, the light pollution is really low up there. And it's easy to just look at really distant stars and galaxies because of it being ideal for data like this. Notable discoveries because of the Keck Observatory is an exoplanet as big as Uranus. I know they found 4 different quasars as well, and a little recent, maybe 2 years ago, was the photograph of Povehi, the black hole that is really cool. It's the name of my car now. So yeah, I looked specifically at the MOSFIRE spectra. There's 250,000 different spectra that was gathered due to this instrument right here in one of the Keck telescopes. And it gathered data from over 150,000 different galaxies, which is a lot to try to narrow down. And a cool thing about this instrument is it's a reconfigurable mask with 46 slits, more on mask later. But essentially this gathered, but not analyzed a lot of this data. So that's what I'm doing. I'm going in and trying to find anything really worth noting. So a galaxy spectra and why it's important. The spectra is essentially the emission lines coming from that specific galaxy. And it's essentially just a fingerprint of what that galaxy has in store for us. With the spectra, we can find out its temperature, density, and composition for it. Basically what it is producing or what's in the galaxy. And it's redshift or blue shift, how fast it's traveling away or to us because of redshift and blue shift. And we can also look at the active galactic nuclei, also known as the AGN. So this particular figure I'm showing you right now has actually helped identify this particular a celestial body as a quasar. So it's really cool work that we're doing. So after like figuring out what I want to look at, I had to figure out where I want to look at in the sky. Like a lot of my peers have said before, this cosmic evolution survey field, also known as the Cosmos field, aims to study galaxies, both its properties, like what's it producing, and the environment, like what's affecting it, related to like galaxy mergers and whatnot. And those are its coordinates in the night sky. And also neat stuff to know about the Cosmos field is it's basically just a big expanse of sky that has little to no, or our Milky Way galaxy has little to no effects on this particular little slit, I guess. where there's not a lot of gas clouds or like stars affecting these far, far distant galaxies. So it's a really good field to look at to identify and classify and try to get a timeline of all these different galaxies and how it's formed. And yeah, essentially the farther back or farther out we look at these galaxies, the farther back in time we look at as well. So we can get a good idea of how our own galaxy has formed. And there's over 400 different papers that reference the cosmos fields in their references and whatnot. And I guess this is another one. So after figuring out where I want to look, I had to figure out the filters and masks that I should be looking at. So the filters essentially filter out specific specific wavelengths of the spectra data, the spectra coming in. And yeah, and the mask essentially blocks out certain light that we don't want to get more precise data. So with all of that, I had to figure out which data to use. So I specifically looked at the H and K filters, which essentially helped look at the red shifting and the red side of the infrared spectrum and whatnot. And looking through the COA database, I found 43 different masked names that has both the H and K filters in it. So essentially I narrowed it down to however many, like 250,000 different data for the spectra into just 43 different masks. So 86 actual file locations and whatnot. And it spanned over 21 different projects. So yeah, it's a good starting point for what I'm trying to do. So once I had all this files and data and whatnot, I had to reduce it using the MOSFIRE data reduction pipeline. And that's where a lot of my problems occurred through this summer. The MOSFIRE DRP was not user-friendly right when getting into it. A lot of the things that I needed weren't there, particularly the AstroPi helpers, which probably everyone generally has, but someone who just came into astronomy trying to get data doesn't really know that until like they have to do extensive like looking up files, looking at Google and whatnot. And a lot of the calibrated files, once having a target in the COA database, were not immediately included. I had to kind of zoom out, look at the program ID to try to get all the calibrated files that these files needed. And a lot of my storage space has gone to each individual mask. One mask can have over 1,000 different calibrated files. So essentially, the analogy I use is the MOSFIRE data reduction pipeline and the COA database were essentially speaking two different languages at each other, and I had to go in and try to translate between them to just get the data reduced. So a lot of my future research that I want to do is to actually analyze these data. I found one of the mask names to have easily accessible calibrated files, the Cosmos C2 IGM is the name of the mask, and specifically the H filter. Currently, I'm working on the K filter. A lot of the K filters are giving me a hard time. But essentially, I want to improve the MOSFIRE TRP. So the next person trying to do this doesn't have to go through all the steps I need to. Just recently, PyCoa, one of the files and software used for in Python for specifically Coa raw data, has just been released specifically for MOSFIRE. I'm looking at that now, trying to see if it'll help through this process. If there's anything I can do to improve it, I want to, but that's for future things. So special thanks to Dr. Kartaltebe for putting up with me this summer and helping me out throughout this journey, I'd say. Brittany helped me get through the MOSFIRE DRP and helped me realize that it's just really weird and it's not just on me. And yeah, and viewers like you, thank you for listening. And here's my references and yeah, any questions.